Study Unit 7, Lecture 4. Lectures 1 to 3 considered switch mode DC to AC inverters, whereas Lectures 4 and 5 will take a look at resonant mode DC to AC inverters. So the reason these inverters are called resonant mode is because there will be some other resonant network which will resonate at a certain frequency, and this frequency is the AC frequency of the output. So shown here are two possible resonant circuits. There is a resonant circuit where all the elements, inductor, capacitor and resistor, are in series, and there are parallel resonant circuits where all of the elements are in parallel. So some characteristics of resonant mode circuits are: one is that the supply current cannot change quickly. The reason supply current can't change quickly is because the DC supply or source will have some output inductance, and this output inductance will limit the rate of change of the output current. The goal of a resonant mode inverter is to design an inverter which minimizes switching losses. So switching losses can be minimized by making use of zero current and zero voltage switching. The primary advantage of having this sort of lossless switching mechanism is that it allows the size of the reactive components in the switching networks to be reduced in size, and also for smaller switches to be used. So there are two main techniques for achieving this sort of lossless switching. The first is to make use of a resonant load that provides a natural voltage or zero current switching during conversion. The second is to make use of a resonant circuit across a switch which will feed energy to both the load and the switch, and on average reduce the switching losses. Recall from the previous lectures that there were instances during DC to AC inverters which made use of switch mode schemes where the switches would experience simultaneous maximum voltage and maximum current during turn on and turn off periods. Resonant inverters allow for these switching characteristics to be different by having zero voltage and zero current switching. In other words, during commutation there will not be a maximum voltage or maximum current condition. The absence of this maximum current or maximum voltage condition drastically reduces the stresses which will be experienced by the switch. So in general there are three types of resonant converters. There are load resonant converters, resonant switch DC to DC converters, and then resonant DC link and forcibly commutated converters. In this lecture, DC to AC inverters which make use of series networks and parallel networks will both be considered. So shown in this diagram are once again the two different network types. There is the series connected network where the two reactive elements and the resistive element are all in series. Then there is the shunt network where all the reactive elements and the resistive element are in parallel. And the analysis, both networks are stimulated with a step function. For the series network, the step function is a voltage step, and for the shunt network, the stimulant is a step current. For both networks, there is some point where the resultant current or the resultant voltage will pass through zero, and these zero crossings are the ideal points at which commutation can occur. The series circuit will be capacitive in nature at low frequencies and inductive in nature at high frequencies. The parallel network, or the shunt network, will be inductive at low frequencies and have a capacitive behavior at higher frequencies. The point at which each circuit transitions from a capacitive to inductive or inductive capacitance is called the resonant frequency. So when the circuit switches at the resonant frequency, it is neither capacitive nor inductive, and it presents a purely resistive load to the input. So for the series network, once this capacitor is fully charged, then the current through the network will be zero. This is intuitive, since once this capacitor is fully charged, no more charge can be transferred across the capacitor. For the parallel network, the output voltage will be zero when this inductor, which is in shunt, is fully charged. When the stored energy in this inductor is at a maximum, this inductor is essentially a short circuit, and thus the output voltage will be zero. It is these two cases which generate these zero crossings in the output voltage for the shunt network and zero crossings in current for the series network. So the current in the series network is given by this equation over here, which has many components. I0 is the initial current when the step function was introduced and stimulated the series network. V0 is the initial voltage over the series network. Omega 0 is the resonant frequency of the network, and omega 0 is defined as 1 over the square root of LC. Alpha is defined as R over 2L, and psi is defined as R over 2 omega 0 L. Psi, or sometimes pronounced C, is the damping factor of the network. This damping factor determines how erratically or how long the network rings when a step function is introduced to the input. In other words, C determines how long these oscillations will occur at the output before the output stabilizes. The voltage across the capacitor is given by this equation. This is important because the capacitor voltage determines how much energy is retained in this series network. All resonant elements will have some or other quality factor Q, which determines how well the resonant element performs. This quality factor is the ratio of the reactive power to the average power in the resonant network. The higher the Q factor, the less real power is dissipated in the resonant network. For these resonant networks, or for the series resonant network, the Q factor is the characteristic impedance Z0 divided by R, where the characteristic impedance Z0 is equal to the square root of L over C, and this is effectively the impedance during resonance of the network. What this means in practice for the series network is that as the quality factor becomes worse, or as Q decreases, then the bandwidth of the network will also increase, and this decreases the ability of the network to resonate. The higher the Q, the more easily that network will resonate at a specific frequency. Also shown on this graph here is that at resonance, the characteristic frequency of the network, then the impedance is equal to the characteristic impedance. And as the frequency increases, then the network becomes more inductive, and as the frequency decreases, the network becomes more capacitive. A similar analysis can be done for the shunt network. Here, the output voltage of the shunt network is defined by the following expression, and this is actually the voltage over the reactive capacitive element. As with the series network, there was an initial voltage and output voltage. For the parallel network, there is initial source current and output current. Omega 0 is the resonant frequency, and alpha is now defined as 1 over 2 CR. In the series network, all the energy was stored in the capacitor, and thus the voltage across the capacitor was important. In the shunt or parallel network, all the energy is stored in the inductive element, and thus the current through the inductive element is of importance. As with the series network, there is also a quality factor or figure of merit for the shunt network, and this is defined as R over Z0, which is the inverse of the quality factor for the series network. Once again, the higher the Q factor, the more effectively the circuit can resonate. The lower the Q factor, the wider the bandwidth of the network, and the less effectively the network can resonate. And this completes lecture 4, which was a very quick summary of LCR networks, both series and shunt. Lecture 5, which is also the final lecture of the study, we'll have a look at how these type of networks can be used to implement a resonant mode DC to AC inverter.